Well, when you finish your measurements or observations, you end up usually with a bunch of numbers, right? So you have a lot of numbers. If you have, for example, let's say 20 individuals and 10 different variables that you measure, you end up with 200 numbers if you talk about numerical data. How to organize these numbers? Well, let's talk about very important things. First of all, it's the modality of your data and dimension of your data. Modality, we will call modality is a number of independent sources of variation. And very also common term to define modality, it's ways. Okay. For example, why your values vary. So why you have this variation of why you have different numbers? First of all, because you have different individuals, right? So if you take one particular property, one particular variable, it's different. It varies from one individual to another individual. That's one way. Okay. The second way, because you have different variables. For example, you measure 10 different variables, and of course, the weight of one individual is not the same as the height of this individual, right? So you have variable to variable variation. If you think about spectroscopy, the absorbance at one wavelength is not the same as the absorbance at another wavelength, right? It also varies from one wavelength to another wavelength, right? So that's another way. So we have already two ways. The third way can be thought of time. I mean, if you fix one individual and one variable, it also can vary in time if you have time measurements, right? So it will be a third way. Then I can actually continue, but I think you got the idea. So modality, it means how many of these ways of variation you have in your data, right? So if you don't do time measurements, but you have many individuals, many variables, then you have a modality of two or two-way data. Dimension is how many independent items you have in each direction. For example, how many individuals you have, how many variables you have, how many time points you have. That defines a dimension of your data. And this, what you see on this slide, is probably the most typical structures, the most typical way to organize your data related to modality and dimension. Let's start with a simple one. So this is just a one number. So if you just have one individual and you measure just one value, you have just one number. And usually it's called scalar or zero-way data because it doesn't have any structure at all. Why it's called scalar? Because usually scalars is not real measurements. Scalars is something that we use to multiply these measurements, scale these measurements. So we use numbers to do some multiplication or some other arithmetic. So it's not a real measurement usually. Okay. Then if you take measurements for many individuals, or maybe you take measurements for one individual and many time points, one individual or many variables, then you have a certain sequence of the values. And usually we organize the sequence either as a column or as a row. And in this case, we are talking about one-way data. You have one way only of the variation, one direction of variation. Then we call this a vector. Okay, this will be a column vector, and this will be a row vector. Okay, usually, again, we use columns for variables, and then we use rows for individuals, and that's what we are going to do also in this course. And then dimension of this data will depend on the number of rows and columns. For example, in this case, you have 5 rows and you have 1 column. So you can say that the dimension of this data is 5 times 1. Dimension of this data, in this case, you have 1 row and 3 columns. So you can say that the dimension of this data is 1 by 3. Okay. Then if you measure, for example, if you have two modalities, if you have two sources of variation, for example, many individuals, many variables, so many individuals and many time points, but one variable, then you organize it as a matrix. And in matrix, you have these two ways, rows and columns, so they can both be larger than 1. And then the dimension of this matrix, we will just simply a number of rows and number of columns, right? So in this case, we have a matrix 5 by 3, 5 observations, and 3 variables. So the dimension will be 5 by 3. Okay. Then finally, if you have if you have modality of 3, if you have, for example, many individuals, and then you have also many variables, and then you also measure these variables in time, so you have 3 sources of variation, independent sources of variation, and that's a 3-way data. Mathematically, it's called a tensor. A tensor can be actually any dimension. Actually, matrix and vector are also kind of tensors. And then the dimension of this data will be, in this case, 5 times 3 times 6, because you have actually 5 rows, 3 columns, and then you have 6 slices, right? So 6 matrices, so to speak. So that's the three-way data. And then, for example, most of the time we are going to use a two-way data. That's how to represent two-way data. It's a matrix. In a normal way, we call it a table, but let's use word matrix. And then to make all mathematical notations like more clear, we will use special letters for that. For example, if you see a capital letter and it's bold, it means it's a matrix. If you see a capital letter, but if you see a small letter bold, it means it's a vector, either column vector or row vector, right? And then if you see it's not bold, but italic, and then sometimes I also use these indices, it means it's a one particular element of this matrix or this vector. For example, in this case, 2, 3 means second row, and 3 means third column, right? So it's an element of matrix X, which is located at second row and third column. So this is the notation that we are going to use in this course, okay? And then I'll give you a couple of examples. A very common way of the two-way data in chemistry, it's a spectroscopic data. You can think, but spectra are curves, right? How we can make it a matrix. But in fact, this is not fully continuous, right? So the wavelengths or wave numbers, we have some discrete measurements, right? So we have, for example, let's say 100 wavelengths, right? Or 100 wave numbers. So it means that we measure absorbance or reflectance at 100 different wavelengths or wave numbers, right? So it means that every measurement actually results with a vector of 100 numbers, right? And then if we do these measurements for several different individuals, for several different objects or specimens, then you can organize it like simply stacking. So you have the first spectrum as 100 numbers, then you have the second spectrum as 100 numbers, the third, and so on. So you get a matrix. And this matrix, as we already discussed, that every column is a variable, and in this case variable is just a wavelength. So you have the first wavelength, second wavelength, third wavelength, and so on. So you have hundreds of columns, and then every row is individual measurement, right? So it's a sample, or it's a measurement that you actually carried out. So in this case, you can see that I have 5 spectra, and then I have 100 wavelengths for every spectrum. So it means that this spectra can be represented as a matrix 5 by 100, which meaning 5 rows and 100 columns, right? And then again, in chemistry and analytical chemistry, you can find a lot of equipment that actually end up with a higher modality data. For example, how GCMS works, gas chromatography mass spectrometer, right? First of all, you may have several individuals, and that's already one way, right? So you have one way, one direction of variation. Then if you take one individual, you have the chromatography, so it means that you have different retention time, right? So you have, this is another way. Second way, different retention time. Then for every retention time, you also get a vector of values, which is a mass spectrum, right? So it's a third way. So strictly speaking, GCMS data, it's a three-way data. You have three different directions of variation. It's individuals, so data varies from individual to individual. It varies from one retention time to another, and also mass spectrum, it means that you have also the variation here. Yeah. So this is how it looks like for one particular object, for one particular sample here. So you can see that you have a matrix of values, because every peak is a value, right? So you have a matrix of values for one individual, and then because you have several individuals, you simply stack it. So you will have a data cube, or a three-way data, a tensor. Okay. So that's how to represent data. And now let's talk about how to actually visualize it. And the most important thing in the visualization is how to actually organize data in a variable space.